Thank you, everybody. So we now have a second lecture from Dr. Patrick Michel. So he's now is the director of at the CNRS, and he's leading the team of the TOP, which is a series observation in parentology, and now he's a PI of the space mission Hera. He will introduce in this presentation. He's also a co-PI for two of the two asteroid samples return space missions, Hayabusa 2 and Osiris-Rex. She also is a co-PI of the CNES DLR rover on board the Phobos sample returns NNS mission JAXA that will be launched in 2024. So okay, so let's welcome Patrick Michel. Now you can give your presentation now.
Okay, thank you. So first, thank you for the invitation. It's a pleasure to be with you today, and I'd like to present you what we learned from the recent missions, which are Hayabusa 2 and Osiris-Rex, regarding these small asteroids, and what is the future, in particular, with the Hera mission, which will, with the NASA DART mission, will perform the first fully documented asteroid deflection experiment at real asteroid scale, and with a lot of new results, as I will show you. So first, I want to just let you see where I live and where I work. So this is a Côte d'Azur Observatory in Nice. On the bottom, you can see on the bottom left, the view is the view that I have from my office on the French Riviera. You are all welcome to visit when you have a chance. We have a marvelous dome, which was made by Eiffel, who also made the Eiffel Tower in Paris. And I'm leading the top team, which is the team that is devoted to the understanding of the origin and evolution of our solar system through various approaches, which go from numerical models and theories to laboratory experiments, instrumentation for ground-based observatories, and of course, space mission. So as you all know, I'm focusing on small bodies of the solar system. And the reason for that actually is not unique, because what is great with those bodies is that they are fascinating for many reasons. And essentially, all these reasons need the same knowledge. So whichever is your objective when you go to explore these asteroids, the knowledge will basically feed at least three communities. Of course, the first one is the science community, because these small bodies are the best tracers of our solar system history, because as you know, they have the record of the original composition of the solar nebula in which the planet formed, and some of them may also contain the seeds that allowed life to emerge on Earth. Then there are planetary defense reasons, because some of them represent a threat. And finally, as you also know, some countries and also companies are interested to explore them, to potentially use them as resources. And essentially what we need for these three reasons is to better understand their characteristics, both their composition, but also their physical properties. And in fact, what we know now, thanks to the past mission, is that we have an extraordinary diversity in this population, which is absolutely exciting and amazing. Object is different, and even on one object, you have a very diverse range of geological features. So these are not just simple rocks in space. They experience a lot of processes which basically make their geology evolve over time, and that's how you can see craters on the surface, boulders, landslides, pounds. You also have some bodies which are active, that particles are ejected, and therefore it's really fascinating, because we are still at the stage where we try to understand what it means. You will see later also that you have different kinds of boulders on a single body, and that's not obvious to understand. And the reason for that is probably related to their history, because as you know, most of these objects are in the asteroid belt between Mars and Jupiter. And in this region, these bodies collide with each other. And therefore, this collision transforms them. Some of them are basically disrupted. Some of them are fragments of the disruption. And then there are, some of them are sent to unstable zones, which we call resonances, which can transform their circular orbit on a more elongated, the Yarkovsky and Yorp effect, more effectively than in the main belt because they are closer to the sun. So we can see they have a very rich environment that basically transform them over time. And therefore, once we have this understanding of the dynamical history of these bodies, finally, there is no surprise that they have a very rich geology on their surface. And in fact, for instance, what we know is that these bodies collide with each other, and that most of the bodies below a few tens of kilometers in size are at least of second generation, which means essentially that they are the fragments of a larger body that were disrupted. And we simulated from the early 2000s this disruption phenomenon, which is actually quite complex when we talk about the big object, because what we realized is that basically the disruption process involves two phases. The first one is the impact of a projectile that through the shock wave that penetrates through the body can generate fragments. But then the process does not end here, because when these fragments are produced, they are ejected, but because they can have a low relative velocity, they can come back together due to their mutual attraction and form aggregates. And this is going to be shown here on these two movies, where on this movie, the green dots are the fragments that have been generated by the fragmentation itself. And these are basically 10 to 100 meters in size. But you can see that when you let them evolve under the gravity, some of them reaccumulate and form aggregates that we call rubble pile. And this movie is centered on the biggest body. But in fact, if I made a zoom out, you would see a lot of aggregates form in that way. And because aggregation is a stochastic process, of course, depending on the bouncing properties, etc., the bodies can have a different shape. So here, for instance, we reproduce quite well the asteroid Itokawa that was observed by the Hayabusa mission. And in fact, we also explain the presence of boulders on the surface because to have so many boulders is not obvious because normally these boulders come to the craters, but there are not that many craters on Itokawa. So what we think is that these boulders are basically the outcome of the reaccumulation that made Itokawa form and therefore are part of the pristine Itokawa. On the left, you will see another simulation of disruption where here the colors are the temperature that are reached by the material due to the impact. We were interested to know how hot the material becomes when the impact occurs to see if we can possibly dehydrate a hydrated body, and therefore it would lose basically the hydration, the mineral, hydrating minerals. But in fact, what we see in this movie is that the temperature, I mean, you don't see it on the movie, but the temperature does not get so high, so you can keep hydrated minerals from a hydrated-crowned body in the rubble pile that are formed from this body, which is interesting because you will see later that Ryugu and Bennu have the hydrated minerals. And here on this example, you can see that the shape is very different. Here we form a more spherical body. Even in some cases, we directly form a top shape, which is a shape that has that is a shape of Ryugu and Bennu. So the bottom line is disruption processes in the main belt can produce a wide range of shapes, and essentially most of the bodies which are smaller than a few tens of kilometers and larger than a few hundred meters, maybe 100 meters or 200 meters, are rubble piles according to these, at least to these models. And this is quite compatible with the bulk density that we have measured for asteroids, which are always smaller than the bulk density of the meteorite analogs, which means that if the density is smaller, there must be some voids to compensate. And the voids can come from the fact that when the bodies reaccumulate together, of course, they don't reaccumulate perfectly. And therefore, you always have voids between the boulders, which explains the low density. But this is one of the processes that the bodies experience. Another one is a Yorp effect, which is, as you know, a thermal effect that can change the rotation rate and also the obliquity of the small bodies due to the change of direction of the heat that the body experienced and where it re-emitted. And depending on the internal properties of the bodies, the outcome of the Earth effect will be very different. And for instance, in this early study, we were interested to see whether you could form binary asteroid by the Earth effect. And you will see a side view on the left, a top view of the simulation on the right. We start with a rubble pile because we believe that most of the objects that are small enough to experience the Earth effect are rubble piles. And you can see that when you spin up the body, the particles that are originally on the pole, they fall to the equator where the centrifugal force is maximum. And when the centrifugal force exceeds the gravity, they can escape and potentially collide together and form a secondary. And the way this mass shedding occurs gives the shape to the body, which corresponds to a top shape. So this was a very early simulation. We have a much more, I would say, realistic one now. And you will see later when I will talk about Hera, what could change. Basically, these simulations are still okay, but it just represents one case and not necessarily the entire range of outcome of the Earth spin-up. So Hera basically will allow us to check, because it will go to visit a binary, which kind of scenario is preferred for binary formation. So this is basically our understanding based on the dynamical processes they experience, the way the process reshapes them. But this is just theory. And we need, of course, observable to check what we predict. And although ground-based observations are crucial to have a first determination of all these properties and a statistical even study, because you can observe more bodies than with a space mission. And I think Joseph Durek made a nice presentation about that. I'm going to present you what we know from these space missions, which, of course, at a higher price, allow us to have much more details, which turn out to be very crucial if we want to understand them correctly. And as you know, we had these two missions, Recherche from NASA and Hayabusa 2 from JAXA, that sampled super successfully two primitive carbonaceous asteroids. And one sample is already on Earth and under study, and the other sample will return to Earth in 2023. So there will be an amazing and a huge amount of knowledge thanks to these two missions. But already they visited these two bodies, and thanks to the observation that were done during their visit and also their interaction with the surface, we really have a new understanding of these little bodies that I will show you. So I will start with Hayabusa 2, which is really a success story, because Hayabusa 2 performed a lot of close proximity operations, each one very challenging, because each time, of course, you want to approach, to take a sample, to deploy a lander, or to make an impact, you take a risk. And all of this was a great success. It's really amazing. And now, as you know, the samples are on Earth and under analysis. So I will, of course, because I just have a short amount of time, I will just cover some of the main things that we found with Hayabusa 2. But of course, I would need basically a full day to present you all the discoveries. So the first thing is that Ryugu, the first images of Ryugu, were the first one in the space history of a carbonaceous asteroid in so many details. The only images that we had of a C-type body were the one provided by the NEAR mission by NASA that made a flyby of Mathilde, which was a C-type main belt asteroid about 50 kilometers in size in 1997. And already there, we saw that these bodies are super dark, probably very porous, because the brilliancy was already estimated to be very small, but we didn't have any details on the surface properties. So these first images of Ryugu were really a source of big excitement when we received them, because we were really feeling that we are exploring a new territory like we never saw before. And effectively, the first surprise was the amount of boulders, which is absolutely very large. As you can see, we have boulders everywhere. That was something we didn't expect. The albedo is super dark, super low, and we started to see the hydration band, which confirmed that Ryugu has some hydrating minerals on this surface. So there was a lot of studies during the first months, because the Japanese wanted to make sampling quite soon, originally in October 2018, after arriving only in June 2018. So we had to do a shape model. You can see here, this is a top shape, which was not necessarily expected based on the light curves. We thought it would be a spherical body, but not the top shape, like for Bennu, for instance. And then you see the spectra, where you can see that the Ryugu spectra sort of look like some of the chondrites, which we call CIs chondrite. And then, of course, the gravity field was estimated. That's how you could measure the bulk density, which is only 1.19 grams per cubic centimeters. Also, temperature maps were done, confirming that it's super hot when it is exposed to the sun. And then the albedo, as you can see, is a very, 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 very low, which posed a lot of constraints for the instrument because this was not expected. And so one of the lessons learned is that when you do a space mission to a small body, because contrary to when we go to see Mars or the moon, we already have basically some knowledge. We don't know anything. So we have to be super flexible in our approaches because we scientists are very often wrong in our assumptions. Of course, because if we go to visit them, it's because we want to learn. So there is no surprise. And therefore, even though we need assumptions to prepare the operations, we have to be prepared to have to change everything when we are on site. And this is what happened with Hayabusa 2. Here you can see these images showing you the fascinating geology that you can see on the surface. You have a trough, you have a ridge, you have many craters also at the equator, a lot of boulders, this Otoimi boulder, which is super big, and we don't even know what it does there. I mean, it's really crazy. And we see rocks everywhere with different morphologies. And that was even more obvious with the Mascot lander. Mascot was a small lander, 10 kilogram, developed by DLR, the German Space Agency, and CNES, the French Space Agency. And Mascot was successfully deployed by Hayabusa 2 on the surface. And you can see these images very striking over the surface, showing you the different kind of boulder that we see, like very porous boulders with layers. We call them cauliflower because they look like they have a sort of a morphology of a cauliflower. And then you have more angular boulders, brighter, with some cracks, so maybe more brittle. And so you see that even one body, which is one type, C-type, it's not as simple as this. We have a lot of different kind of boulders. And so the first sampling occurred in 22nd February 2019. You can see the technique. I think you know that. It was a touch and go approach. So the aim is to stay as very short amount on the surface, only 1 second. And with a sample horn, when it touches the surface, then a small projectile of 5 grams launched at 300 meters per second impact the surface, and we collect the ejecta produced by this small velocity impact in 1 second. And the target was to have 100 milligrams of samples. And you can see here the sample horn as it is, with also some little things here that could also grab some pebbles. We try to grab everything that we can grab because the aim is to collect samples. However, they had to change the approach because the original approach was allowing to have a landing accuracy of a few tens of meters. And the problem was that we discovered that there are so many boulders on Ryugu that we cannot find any area as large as a few tens of meters that doesn't contain boulders. And therefore, the only thing we could find was areas which were large at most by 10 meters. So the original strategy, which was to deploy a target marker and then to follow it while it descends on Ryugu, had to be changed because that only allowed to have a few tens of meter accuracy, which seems in principle reasonable, but not enough when we were there. So instead of that, the Japanese decided to find another strategy, and they were really fantastic. This team is really fantastic. And the first thing was to deploy on the surface a target marker in or close to the area chosen for the sampling, and then use the target marker on ground as a reference to then land. And with this, you have a much better accuracy. And so here you can see the landing, the sampling site selection, selected sampling sites that you can see here. So there were 2 sampling sites. One was L08B1. As you can see, it's 12 meters wide. But then eventually the target marker was a little far away, and there was another zone of 6 meters that was eventually chosen, although it's much smaller, so much more challenging, because you can see that around you have boulders, and the target marker is not exactly in it. But the Japanese knew they could deal with that. And you can see here the advantage of this small zone is that it has rocks which are less than 60 centimeters in size, so that's safer. So either you choose a larger area but with more rocks, or a smaller one with less rocks. And the Japanese decided to go to this very small zone, and therefore in order to be able to be prepared, they had to sacrifice a first sampling that should have occurred in October 2018, and to then go for the sampling in February 2019. You can see here again the zone from the top, very small, noting that we are at 300 million kilometers from the Earth. And here you see the movie that was taken, where you can see the sample horn here, and when it touches the surface, the projectile is deployed, and we only see, of course, what is ejected outside the sample horn, but there are so many ejecta that we already knew we should have taken a lot. And the thing which is really amazing is that they only landed at 1 meter from the targeted point, which is nothing. So it's really a fantastic success. And then we did numerical modeling of this sampling process with our granular code with my student Florian Thuillier. And what we found is that we were trying to reproduce the ejecta field that we could see from the outside of the sample horn. And with the modeling, we could measure how much was taken inside. And we were predicting that it would be possible maybe that they collected 1 gram, while the target was 100 milligrams. But of course, it was just theory. And we had to wait the return of the sample, because there was no way to measure the samples in the spacecraft. So that was a fantastic success, which was, of course, celebrated. It was the first in the space history that the sampling of a carbonaceous asteroid was done. But the Japanese were not, just waiting for this. They wanted a new challenge, and the other one was even crazier. That was this small carrion impactor experiment, which consisted of exploding a box which released a 2-kilogram copper projectile at 2 kilometers per second to make an impact on Ryugu, and therefore to both check our understanding of the impact physics on an asteroid, and also to possibly relieve the interior and take a second sample, which could possibly contain a fresh material that was not exposed to the solar radiation until the impact occurred. So I was in the operation room during that time too, because I was part of this impact experiment, which was really fantastic and scary. And you can see here the explosion of the box seen by a small camera that was deployed to observe the event while Hayabusa 2 was going far away to get protected from any possible ejecta. And then we had the movie of the impact itself, where you can see here the ejecta that are produced, and the big surprise that some of them come back on the surface. And this is a big surprise because we impact at 2 kilometers per second, and the escape velocity of Ryugu is only 20 centimeters per second. So we were expecting that most of the ejecta would fly away, because if they come back, it means that they are ejected at a speed which is smaller than the escape speed of 20 centimeters per second, which is super low. And unfortunately, in the numerical models, it's very difficult to track these super low speed material. And on Earth, because we have Earth gravity, we cannot assess the possible production of very, very low ejecta. So that's why we could not predict what could happen for the low velocity ejecta. And we are really surprised that there are so many ejecta coming back. But it was a good news, because the aim was possibly to take a second sample with grains coming from the inside. And therefore, with this ejecta blanket, we had a better chance that it happened. So that was already a big surprise and a good news, I would say. Of course, we celebrated again, and this is very important because I really think that the human experience is also a fundamental experience in the space exploration, because we are basically a family aiming for the same challenges and the same knowledge, and it really unify all the people together around the world. And I think that's a very important message, especially during these current times. So it's very important to show this international cooperation working so well. And then later on, 2 weeks after the impact, Hayabusa 2 came to observe the crater size. And again, another surprise, the crater was much larger than we expected. It's about 50, I write 15, but it's maybe 17 meters in size. And we were expecting something like 2-3 meters in size. But the thing is that, in fact, the reason why it is so large is because, I mean, this is the only interpretation, the surface has no cohesion. If you cancel the cohesion from the equations, you can reproduce this large crater. And this is a little surprising because when you see the left image, you have a lot of boulders. So you could expect these boulders of some strength. And some of them have some strength because some of them survive the impact. And yet the body behaves like it is a fluid. So there is something that is really strange. We believe now we have a better understanding why, but we need to have this impact experiment to realize that we have a problem in our impact modeling and that we possibly have to take into account some other processes, which we are now doing. And but the bottom line is that the body behaves like it doesn't have cohesion, which is a big surprise. And also by comparing the spectral color before and after, we find that the surface is bluer than before in the crater, which means that a fresh material is bluer than an old one. So old one, with time, it becomes redder and redder. So now what we want to see, what will happen with DART and Hera, as you will see later. The target is much smaller, the impact speed is greater, and therefore we may have a lot of surprises again. And finally, for Hayabusa 2, of course, the success was even higher than we thought when we weighted the sample that came back to Earth, and we have 5.5 grams while we were hoping for 100 milligrams. And the bulk density was already measured, and it's very low, much lower than any meteorite that we have in our collections. So these samples are unique. We don't have them yet in our meteorite collection. Their composition look like the composition of CI chondrites, but they have differences which show the importance of getting there to get the samples so that we add new knowledge compared to the meteorite, and we can also place in a better way our meteorite collections in asteroid science. So total success for Hayabusa 2. We learned a lot. We have a body which is very exciting, and we are still trying to understand many of the data that were received. So these missions can make many generations work on the same data, and for the samples even more, because 60% of them are kept for the future generations. Then in parallel, we had the OSIRIS-REx mission, which was launched a little later than Hayabusa 2, but there was an overlap between the two missions in terms of operations, and it was really, again, a great example of international cooperation because some of the team members were in the two missions, and that was not a problem. On the contrary, there was a clear and transparent exchange of information. And it's really, for me, the message that when we work for science knowledge, the frontiers are erased, and we are all excited to participate in the adventure, and we accumulate our expertise together for the best, which I think is very important. And you can see the first images that we got from Bennu in December 2018, and again here it's a top shape. This was expected from radar observations, contrary to Ryugu, but I mean, it was striking to see that Ryugu and Bennu look almost the same, at least from the first images. Then we found some differences. And of course, the size is different. Bennu is only 500 meters, while Ryugu is about 900 meters. But apart from that, the albedo is the same. The bulk density is the same, 1.19 grams per cubic centimeters. We have also craters at the equators. We have boulders everywhere. So it's something that really was very confusing for us and exciting, of course. But then the next thing, which was totally crazy, was when we found some ejecta, particles ejected from Bennu. So Bennu is active. There are particles that are emitted. We have various scenarios to plane them, but none of them is confirmed. And you can see the trajectory of these ejecta. Some of them come back on the surface, possibly re-emitting new ejecta. So it's a very active asteroid, not only because there are some surface motions like on Ryugu, but also because there is this activity, which is something that we did not expect at all. And here you can see the images taken with a very different approach, because Hayabusa 2 was hovering, so was kept at 20-kilometer distance from the asteroid, and then coming sometimes to make some close proximity operations. In the case of OSIRIS-REx, the strategy was to go into orbit around Bennu, so totally different, with some very close flybys, which allowed to have superb images. And the camera had a quality which really strikes me all the time. And I keep looking at these images and zooming because you see so many things on them. You can see here this very angular boulder compared to these more rough one, very dark, and some bright spots. So it's really, you can spend a lot of time on them, and you can find many of them on the website of the mission. For the geologist, it's like a dream. A lot of things that can be understood from these images. But you can see the variety of the boulders and the wide distribution, which pose the same problems in terms of operation. And again, here the OSIRIS-REx team had to revise entirely their operation strategy, because again, the same assumption was done: 50-meter landing accuracy, and now we have to shrink to 10 meters. So they had to revise their approach, and they didn't have a target marker. So they had to do it completely differently. So it was very interesting to see the two teams trying to find a strategy with the same constraints, but not with the same equipment. And eventually, on October 20, 2020, the sampling occurred. And here again, the surprise was that even though the image before the sampling showed boulders on the surface, the sampling tool, which we call the TACSAM, touch and go sampling mechanism, did not feel any reaction from the surface, or a very teeny reaction from the surface. And this is shown here. You can see here the small displacement of material on the right image. But when we measure the acceleration, it's like if it went into melted butter. And again, when you see the images, it's not obvious. So for me, this is one lesson learned, is that you cannot trust images to infer the mechanical properties of the surface. Unless you touch, you cannot know whether the boulders are weak or whether they have some strength. Because even a teeny amount of cohesion, since there is no gravity, can let a boulder look like a boulder. But of course, when you touch it, because the cohesion is super low, then it goes down. So you need to touch to understand that. And for me, this is really the main lesson, is that when you do a space mission to a small body, of course, images are crucial, but having a way to touch, to feel how the surface responds, is very important. Otherwise, you will have an ambiguous interpretation. And in the case of Bennu, what we found also is the surface is redder after than before. So younger means redder. Remember, for Ryugu, it was the opposite. Younger means bluer. So this is why these bodies are really turning our understanding on its head, because things are not as simple as we thought, and we need still to understand better what these contradictions mean. Another thing which is interesting is that this impact process and the fact that the craters are larger because there is no cohesion is very important when you want to assess the surface chronology. The way we estimate the surface age is by counting the craters, measuring their size, and estimating how much time you needed to accumulate them. We call it the crater retention ages. How much time has passed to see all the craters that we see. And for this, we need to take into account various things. First, whether there is cohesion or not, because the crater size with respect to the projectile size will be very different. And also, whether boulders can do some armoring, which may reduce the number of small craters, because if you have a rock which is as big as the projectile would just break the rock and not leave any crater. So when you take all this into account, you can see, and that's what we have done with Bennu, that the surface age can be very different. The first estimate gave a surface age of about a few 100 million years to 1 billion years. And thanks to the revision of this understanding and to new scaling rules to relate crater size to projectile size, we reduced the surface age by a factor of 15. So 1 order of magnitude, which is not small, which has big consequences on the asteroid history. So this is really important to understand this impact process because it has a lot of implications. One is, of course, surface chronology. The other one is planetary defense, as you will see later. And then we also found that the surface is renewed regularly by various processes because Bennu age is at least a few 100 million years, and the surface age is much younger. So it means that this surface must be renewed by some processes. So again, when I say these bodies are active, I mean active not only because particles are ejected, but also because their surface changes all the time due to motion, due to cratering, also weathering, etc. And we are still trying to understand that more globally. So lessons learned are that small bodies are extremely sensitive to cohesion. That was one of the things I wanted to tell you, that, as I said, depending on the level of cohesion, things don't move, and you touch them, it moves totally. And also, it seems that these dark bodies don't have much cohesion, which is also interesting. And as I said also, to determine the strength and the mechanical response, you need basically to touch the surface. This is important. The surfaces are active, and the collisional process needs to be well understood for the various reasons that I said: surface age, the collisional history, and planetary defense. And I'm going to come to planetary defense, but insisting really on understanding collision in space is fundamental because collisions played a key role during all the history of the solar system, from planetesimal formation by collisional accretion to planet formation again by collisional accretion to giant impacts, which are another kind of collisions with a much more violent, like the moon formation and the oh, sorry, I think I have a problem. Do you still see my presentation? Yes. Yes, for the moon formation to giant impact. And now we are in an era of collisional disruption, which basically destroy all the bodies or leave a crater on the surface, which is another thing very important. So let me now tell you about IDA international collaboration, because this will be another impact experiment that will allow you to really understand collisions at a speed which corresponds to the average impact speed between asteroids, and verify our numerical models, and of course make sure that this kinetic impactor technique, that is one of the techniques that is sought to, for planetary defense, works. So this collaboration supports the development of both the NASA DART mission and the ESA Hera mission. So DART was launched in November 23rd, Pacific time, from the Vandenberg Air Force Base in California. It was a superb launch. And the impact will take place on September 26 this year. So DART is, will impact, but before doing the impact, it will release the Italian CubeSat called Licia Cube that will observe the first instant before the impact and after the impact, and give us first knowledge of the early ejecta emitted by the impact, which is super interesting. And then Hera will come on the crime scene and will fully characterize the impact outcome as well as the binary asteroid itself. So that is about 585 kilograms, and the impact speed is about 6 kilometers per second, noting that the average speed between asteroids is about 5 kilometers per second. So we can really use directly the knowledge brought by this impact to study asteroid collisions, which I think is really nice. And Hera will come to measure the outcome of the impact at this scale, and in particular, all the information that unfortunately DART and Licia Cube cannot provide, which turn out to be crucial. So here is the plan for the DART. The Dimorphos is about 160 meters in size. This is a small moon of Didymos, which is about 780 meters in size. And the plan is to deflect the orbit of the Dimorphos around Didymos, which period is about 11.92 hours. And at minimum, we should see a change of 73 seconds. and maybe even more. Maybe a few minutes change could be produced depending on how much momentum is transferred to Dimorphos, which depends on its internal and physical properties. Then Hera and ground-based observations will measure, by the way, the change of orbital period from the ground. So there will be an international campaign after the impact to make this measurement. Then Hera will launch in 2024 and will perform the impact, will arrive at the target at the end of December 2026 and will perform 6 months of proximity operations to characterize the whole system. And this shows you a small movie where you see the DART impact and then Hera arriving 4 years afterwards, which don't change what we want to measure. The crater size will be the same, the mass of Dimorphos will be the same, so we can still wait 4 years after, even though we would have liked to be on the same time, but the European Space Agency did not get the approval for that in time. But we'll have a lot of firsts because the binary asteroid Didymos is really exciting. We'll have the first rendezvous mission to a binary asteroid with Hera. There will be a NASA mission called Janus in the Scientifique program that will make 2 flybys of binaries before Hera arrive at Didymos. But this will be the first rendezvous. And Dimorphos is very interesting because 160 meters mean that it is the same size of Hoteime Saxum, which is the biggest boulder on Ryugu. But we never saw a body of this size in space. So what does it mean to be of this size in space? We don't really know. And we'll have a very first probing of internal properties. This has never been done before on an asteroid. By radar, we'll probe the internal and the subsurface properties directly of the asteroid. And of course, we will fully document the impact experiment done by DART. To do that, we have a spacecraft which has various payloads on the spacecraft, which is, of course, we have cameras, we have a LiDAR, we have a thermal infrared imager provided by JAXA. So we have a Japanese instrument, which is great for the international cooperation. We have an hyperspectral imager, and we have 2 CubeSats that will be deployed, CQ CubeSats that will be deployed at proximity. And one of them will be devoted to the internal, the composition of the body and the subsurface composition by looking at the inside of the crater left by DART. So we can compare the subsurface with the surface, which is interesting, and also a dust detector. And then the other one called Juventas has this low-frequency radar that will allow us to probe the internal properties of the body, which have a higher influence on the impact outcome. So if you want to interpret correctly the impact outcome of DART, we need this information. And then we have a gravimeter that will be deployed on the ground and will give us an even better, higher estimate of the gravity field. And we have also a radio science experiment that is very important because one of the primary objectives of Hera is to measure the mass of Dimorphos, which comes into the estimate of the quantity, the momentum transferred by DART. If you want to validate the deflection and to have a quantitative measurement of the deflection, having the change in the orbital period of Dimorphos is one parameter that will be measured by ground-based observations after DART, which is already great. But if you want to have a direct estimate of the exact momentum that has been transferred to Dimorphos, you need the mass of Dimorphos. And only Hera will give you a direct estimate of the mass. That's why it's really important to have Hera to really fully confirm the deflection efficiency of the DART impact. And then we want to validate the models of impact. And for this, we need to have the initial conditions, which will be given by DART, but also by Hera, that will give you the structure of the body and the physical characteristic. And then you need to have the final outcome, in particular, the crater size. Because with the momentum transferred, it's not enough. You can have an ambiguity. You also need the crater size in order to have the numerical models being validated fully and make sure they are able to capture the physics of the impact at the scale of an asteroid in its low gravity. And talking about low gravity, Hera will go down in gravity compared to the previous missions because it will it is 3 times less wide than Bennu. And we have seen that Bennu and Ryugu challenged our understanding of physics because the way they reacted was not the one we expected. So what will happen with Dimorphos is something very interesting for the impact by DART, but also because we land the CubeSats at the end of the mission and measure the bouncing coefficient. So this will allow us to understand how some processes scale with gravity down to this low gravity of Dimorphos, which is actually very, very low. Another interesting thing is that when you look at the spin period over diameter of asteroids, you can see we have two regimes. One is a strength regime at small size, where the spin rate can be quite fast and the body survives because it has cohesion. And then at larger sizes, because these bodies are dominated by gravity, once the centrifugal force exceeds the gravity, they cannot survive. And therefore, you have this spin barrier that we call spin barrier, because it means that you cannot exceed this centrifugal force that compensate the gravity, and therefore we believe they don't have any cohesion. Dimorphos is in the range which is intermediate between the two regimes. So we cannot basically understand Dimorphos properties from this graph because you have this ambiguity. We need to go there and measure it directly. Another interesting thing is that Didymos main, so the primary, is also rotating quite fast at 2.26 hours. And depending on the actual density, it may be stable or not. It may need cohesion or not. You see here the slopes for a 2.1 gram per cubic centimeter density, which is still within the range of possible densities, and a slope for 2.7 gram per cubic centimeter. So what we find is that in this range of possible density, it cannot survive without cohesion. You will need a much higher density. And we looked at that with my former postdoc, Yun Zhang, which found that effectively to have a body stable depending on the packing of the boulders that make Didymos if it's a rubble pile, you see that if you don't want to have cohesion, you need a density that is much higher than the estimate range for the actual Didymos. So we did some studies about what kind of cohesion we need, and what we discovered. So this is a better approach than the one I showed for the binary formation. Now we can extend to much wider range of parameters. You can see that depending on the bulk density and the level of cohesion, if you spin up the body, it would evolve very differently, whether it is dominated by strength or dominated by gravity. It can fission, it can shed mass, or it can remain more or less stable. So it's very important to understand the cohesion of these bodies, because you can see it has a very different influence on the history of the body. And we are talking about very small cohesions, because 3 Pascal is nothing. 1 Pascal is about a leaf on my hand. On asteroids, such a level of cohesion makes a big difference. So that's why we really need to capture all kinds of information we can have on the cohesion of these bodies to understand the history. And finally, these CubeSats, as I said, will bounce on the surface, and with accelerometers, we'll be able to measure the bouncing coefficients, which are another kind of information about how they they respond to an external action. And as you know now, I hope I convince you, they have a very counterintuitive response. So we need to directly interact with them. So I will finish with that, just saying that, okay, Hera has a lot of firsts. I think I already told you that. And the final message is images are crucial, but they cannot tell us all about those bodies, because already it's something, but if we need to touch. And by the way, after we have touched many times, many images will be enough, because we have a better understanding from images what it means in terms of the properties. Then that's what I wanted to say. We need to keep interacting for now, at least, to know the asteroid response and strength. We have seen that the surface of dark type small asteroids like cohesionless medium, at least Bennu and Ryugu. Is it the case for all dark types? Are they representative? It's maybe too early to determine that, but there seems to be a pattern which may be common. So it shows that making a few missions may allow you to generalize to a whole population. And then low gravity bodies are sensitive to cohesion at very low level, and DART and Hera will give us new information in very low G regarding the impact process, regarding the physical characteristics of binaries, how they form, how they evolve, and regarding also the composition, fresh versus older surfaces. And with this, I thank you very much, and I can take your questions.
Okay, thank you, Patrick, for giving such a very good presentation for those 3 actual space missions for the Hayabusa 2 and Dawn and Hera. And any question from the audience, or you can type your question in the chat box. Okay, so first is Huang Shaoyu. Okay, please.
I'm not from engineering background, so I might have a silly question. It's about the possibility of building a rover. It's like Perseverance on Mars for those asteroids. And for the challenge I could think about right now would be low gravity and soft ground. But if these could be tackled with, then I believe in situ sampling could bring a lot of data to us. So is there any other challenges that needs to be solved?
Well, that's a very good question. It's true that if we can have surface packages, rovers, lander, that's excellent. And in fact, this is what we plan to have with the MMX mission, where we develop a rover, which effectively one of the aim is to demonstrate that we can roll on a low gravity body, which is not something very obvious. We may sink, we may slide, and even that already allows us to add a lot of new information. And that's why we put on the rover a camera that will observe how the regolith flows on the wheels in order to effectively understand how granular material in low gravity evolve around wheels and what is their dynamics. So that would be fantastic. And once we are able to make sure we understand well and we can do rovers like this, of course, you can plan to have a more in situ analysis, or even you can use them to take a sample that you can then put in a spacecraft possibly. So that opens a wide range of possibilities. But I would say the first challenge is, well, of course, first to deploy the rover correctly so that it stays on the surface, and then to learn how to roll on these low gravity bodies, which can have a wide range of granular properties. It's different to roll on a very cohesive medium, or it's different to land on a cohesionless one. It's different to learn on gravels. So I think that's, for me, very important to take these kind of risks, to learn how to design the wheels, etc., for these low gravity, so that effectively we can do many more measurements on the surface.
So it might be in the form like a car, right? Like a vehicle.
It's like it's like a vehicle. That's what we are doing for MMX. It's a rover with 4 wheels, and of course it will roll very slowly. It won't do 10 kilometers. Well, Phobos is not even. We are targeting a few meters. So that's one way to roll. And I think that would bring a lot of knowledge. That's why it's my favorite approach, although it's more complex and risky. The other one is to do what Mascot did with Hayabusa 2, which is a mobile device. Like you have a box and it has an arm, and then the arm can basically relocate it elsewhere. And that way you can relocate, because you are in low gravity, so it's kind of easy to relocate, or do like the Minerva did with these small needles. These are hoppers, basically. It depends what you want to do. But if you want to have a wide range of instruments, like on the rover for MMX, we have a Raman spectrometer. So Raman spectrometer really needs a rover, something that can stabilize, and then you shoot your laser, and then you go to another site by rolling, and then you do it again. So it really depends what you want to measure. The rover is more complex, but it allows you possibly to do more measurements.
Good afternoon, Professor. So I have one question. We know the dust and rock in the moon surface is very thin. Their boundaries are very thin, just like knife, because they are impacted and damaged by the universe radiation in microasteroid. But in Osiris missions, they insert a simple image. Seems like that asteroid surface, the rock is smooth. Their boundary was smooth. It is not very thin. So what will be this happens is because it's a rock are protected by something, or they has their boundaries are damaged by the frictions and move between the rock and the rock. So whether boundaries are not so smooth. So this is my question. Thank you.
So you are saying the surface is smooth? I'm not sure I understand what you mean by smooth, because on Osiris-Rex, I mean on the Bennu and Ryugu, the surface is actually super rough. We don't have, if you to say we don't have fine regolith, that's true. That's something that we still try to understand. We have various ways to explain the lack of fines. So effectively, it's confusing that there are not that many fines. However, what's striking is that even though the surface is rough in terms of boulders and gravel, once you touch it, it behaves like almost cohesionless material. So you turn it very simply into smaller grains, which is contradictory, because if that's, we see that, and on the other hand, we don't see many small grains on the surface. So where do they go? That's something we don't know. But I don't know if I understood well your question and if I answered. But if you want to indicate that the moon is very different than the asteroids, that's for sure. And that's something we still need to understand.
I mean the surface of the rock, but not the surface of asteroid. Because the slides you showed is the rock in the Osiris, they're simple, they're rock. Their boundaries is smooth and sleek. It's not very thin, just like the moon, their surface dust. So what will be this happening?
Yeah. So that effectively, I see what you mean now. Yeah. The surface is we don't see many. We don't see small dust on the surface, and that's something again we don't really know why. We have to be careful with the resolution also, because the very fine dust we wouldn't see it. But it's true that even the mascot lander did not see any small grains. So there is one interpretation that maybe thermal fatigue could allow to in particular for the porous rocks to break them, and maybe the small grains are falling down and we don't see them anymore. So that would be one way to remove the dust. But there is no, I would say, firm answer to your question. It's still something that we don't understand well, effectively.
Okay, thank you, Professor.
Okay, so any more questions from audience or in chat box? Okay, so I have some questions for you. So you mentioned Bennu is some kind of active asteroids. So because there are some particles ejected. So do we know, or I missed something? Do we know the mechanism for this? Okay, so because rotated or something, I don't.
You mean why it is a rubble pile? What it is?
Why those particles can be ejected?
You mean the ejection of particles? Yes. Okay. Yes. So for the ejection of particles, there are, I would say, two main explanations that we have. So the one is simply the micrometeorites that hit the surface, and therefore they generate ejecta, because when there is a small impact, you have ejecta. If this explanation is correct, that should apply to all asteroids, because all asteroids experience micrometeorite impact. And in fact, we looked into that when we found, that's Bill Botke, we did the analysis. He found that effectively the frequency of the activity is about the same of the frequency of impact of micrometeorites. So there seems to be a link. But if this is correct, all the asteroids experiencing micrometeorite, we should see that on all asteroids. And in fact, what we found is that the reason why we didn't see with the NEAR mission or with the Hayabusa 2 mission this activity is because we couldn't, because the cameras did not have the sensitivity to see such small particles. The cameras on Osiris-Rex are fantastic, and these are spectacular. So it's not, unfortunately, because that would be a way to discriminate this scenario. We cannot discriminate it simply on the fact that we didn't see that on the other bodies, because on the other bodies, we could not see them even if we wanted. So that's one explanation. The other one is because Bennu has a thermal hydrated minerals. Then it's possible that due to the solar heat, and there is a sort of a thermal dehydration that occurs. So basically, you experience some heat, you dehydrate a mineral, and that release basically a vapor, and then the pressure can make a puff, which ejects small particles. And that also is another possibility because there is hydrating minerals, and we made actually with Guy Bourrel in Nice some experiments on thermal fatigue of hydrating minerals. And we saw that when we put hydrated meteorite in a oven and we make it experience thermal fatigue, first it cracks more easily, but also it loses mass because you lose the water. Therefore, it's also possible this is the case. So some people prefer this scenario. The other one cannot contradict the micrometeorite one, but unfortunately, we don't have a way to discriminate between the two. There are other possibilities, but these are the two main scenarios that we have.
Okay, thank you. So I have another question. So you say the Hayabusa gave the impact with 2 kilometers per second to the surface. So for the drop, you say there will be 6 kilometers per second for the impact velocity. So do we expect any impact the size of the impact craters, or will be larger, or it depends the properties of these asteroids?
That's a very good question. Yeah, we are going in another regime, like 6 kilometers per second is very high. And thanks to the new knowledge that we had from the Hayabusa 2 impact, we revised our numerical models to make sure that we capture all the physics. And what we find now is that depending on the properties of Dimorphos, the outcome may have a much wider range than we expected. So we could have a crater of a few tens of meters in size, but we could also, if there is no cohesion, totally reshape Dimorphos, even without leaving a crater. We didn't find yet a solution where Dimorphos is disrupted, and therefore we would have a ring around the Dimos. That would be exciting for Hera, but we wouldn't see a body. So we didn't find that yet. But we found that effectively the crater, if it has a lot of cohesion, the crater could be as small as a few tens of meters in size, 20 meters, for instance. But if the cohesion is super low, then we may not even leave a crater, but basically totally reshape the body. And in that case, even make a higher deflection. So that's why I think it's very exciting, because we realize now that the outcome of that may be very surprising, because it's very sensitive, and especially for these very low body, very small bodies, is very sensitive to their physical properties. So we'll see.
Okay, thank you. So are there any question for? So before that, do we know the? You say we don't know Dimorphos type or taxonomy, or we don't know.
We know Dimorphos type. We know it's an S type.
S type.
What I didn't say is that apart from the size, we know nothing.
Okay.
Because all we know is about Didymos, the main, and we have a mass estimate of the binary, and then we assume the density of the two bodies.
We don't know the shape, but I think from Joseph Dolish, he say probably for the binary system, they have a shape. So I think for the Didymos, we did have a shape. So, but you say we don't.
We have a shape for the main, for Didymos prime, but not for the secondary.
Okay, so because it's hard to get the accuracy like or something, or
because the primary dominates. It's 800 meter. Dimorphos 160 meters.
100, yeah.
So
it's too small.
Very, very small. So there are campaigns in order to try to constrain a little more, but we have, I don't think we'll have the shape before the encounter. Joseph can also say more if he knows more, but I'm pretty sure that unfortunately there is no way to get the shape.
Okay.
So DART will give us the shape, and then Lichia cube, if it survives, will go around, and therefore we'll have also the backside, and therefore we'll have a volume estimate which is a better constraint.
Okay.
Professor Ip is back.
Yeah, I think that there is, because sorry, I have opened two.
It worked.
Yeah, it worked now. It was working now. So one thing I always want to ask you, Patrick, that is, we know there's a famous thing called spin cutoff, right?
Yeah.
And indicating that the rubber pie structure of the asteroids. However, what I'm curious is that how do the asteroid know that they should stop at this 2.2 hours, unless they have the same mass and the same. Of course, you would say that they have the same average mass. That's why you have 2.2 hours. But then how do they know that they should have the same porosity in case they have the same composition?
Yeah. So no, in fact, okay. So when we say they are rubble pies at large size is not necessarily correct. What we say is that at large size, the cohesion is negligible, and therefore they are dominated by gravity.
Yeah. Mm-hmm.
Which doesn't mean they are rubble pies, because even a large monolithic object has basically no cohesion. That's based on the extrapolation of what we see on rocks on Earth. A bigger rock has a lower strength than a small one, simply because it has larger flows inside that make it weaker. So if you take two samples, one of, let's say, 10 centimeters, another one of 1 meter, and you heat it with the same energy, the one of 1 meter will break more than the one of 10 centimeters because it has larger flows. So if we extrapolate that to objects of 1 kilometer or 10 kilometers, they can be rubble pie, but they don't have to be. They will be dominated by gravity anyway because the cohesion is going super down. So at the end, what will count for the survival to the spin period is the competition between the centrifugal force and the gravity. And even if you vary the mass or the density, it's not exactly 2.2 hours, but it won't have a much difference. So that's why you have this spin barrier at about 2.2 hours, but it's not a straight line. So it's just a competition between gravity and centrifugal force.
And the second thing is that why should the S-type asteroid have the same spin cutoff like the C-type?
Because again, it's a question. Because even if it depends on the density of the S-type and of the C-type are not that different. It's a factor 2 or something, not more. So when you put that in the equation, at the end, the spin rate at which they break is not that different. So that works. I mean, there is no surprise as long as we don't have any cohesion in the system. If you just have the gravity, you can scale the spin period over diameter and show that effectively everything matches on one line. That's in Kissel's Apple work, who you know, by the way, very well. He demonstrates that quite well. But the key is really to understand that what matters at large size is gravity with respect to centrifugal force, and nothing else.
Okay, good. Thanks.
What was also interesting is what Kissel's Apple, is that for the fast spinners, you don't need much cohesion for them to survive. So that's what I was thinking. The sensitivity to cohesion is much higher than we thought, because even a teeny amount of cohesion makes you survive a fast spin. So on one hand, you don't need cohesion at the large scale to be dominated by gravity, but on the small scale, you don't need to be perfectly monolithic. you can be an aggregate with weak bonds, and that may be enough for them to survive. As I showed in my presentation, when you vary by 1 Pascal the cohesion, you have a totally different behavior, and 1 Pascal is nothing. It's,
yeah, it's amazing. I mean, in the microgravity situation. Yeah.
Yeah, exactly.
No. So unimaginable. Yeah, thanks.
Absolutely. It's totally counterintuitive.
Right. So that's why I need to go to Asteroid and visit them and do all kind of things to to learn more.
Exactly. So that we can develop models, compare them with observable, because models remain models, and we'll still have a lot of surprise because we are still at the stage where we discover this sensitivity.
Okay, thank you. Yeah, thank you. Yeah.
Thank you. It's great to see you.
Well, look forward to seeing you in Taiwan.
I would love that. We have to do something. I'm going to the IAU General Assembly in South Korea.
Okay,
but I don't
maybe you can swing by,
No, this time I cannot, but I would love to come.
Right.
We should plan something. Yes, of course.
But maybe I will ask Zhongyi to organize an asteroid meeting. Yeah.
That would be great. Absolutely.
All right. Good. Maybe next year, right, Zhongyi?
Next year, yeah. Okay. Try.
Okay, thank you, Patrick, and until next time.
Yeah, it was an honor to be here, and I thank you for the invitation, and I was super happy to see you. It's really
okay,
great.
good, and best luck of your mission. Fantastic.
Thank you.
Yeah.
Thank you very much. Thank you.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.